And let's see, we started talking about gases and gas laws. So we talked about atmospheres, which is a very common unit of gases. It is related to some other very common units, which are torr and millimeters of mercury. And remember that sort of the conversion between these three units is that 760 number. So again, if you do have atmospheres and you want torr or millimeters of mercury, and again, a torr and a millimeter of mercury are basically a 1-to-1 conversion. So they're basically the same thing. We are going to multiply by the 760. So multiply by the 760. The atmospheres will cancel, will give us torr. And obviously, if you have either torr or millimeters of mercury and you want atmospheres, we're going to actually divide by the 760 to do that. And that will give us atmospheres. We started talking about gas laws, I believe, and we started with the idea of Boyle's law. Remember, Boyle's law dealt with pressure and volume, holding temperature constant. So P1 V1 equals P2 V2. This is at constant temperature. And the relationship that we saw with Boyle's law was pretty much as one goes up, the other goes down. So when we do have a very small volume, that means the gas molecules have a very small area to fly around in. And what that's going to do is increase the number of collisions. And by increasing the number of collisions, we would see that the pressure would go up in that case. And vice versa, if we sort of increase the volume, what we will actually see is the pressure will go down. Again, by increasing the volume, it's going to give everybody a lot more room to fly around in. It's going to cause less collisions to occur, and we will see the pressure start to come down. I think we then got into Charles' law, I think, as well, which is volume temperature relationship. And in this particular case here, we're holding constant pressure. We also saw one that is related, which is Guy-Lussac's law, which is P1 T1 is equal to P2 T2. And once again, this is at constant volume. So sort of in these situations here, if we look at this one here first, if we increase the temperature, our gas molecules are going to be flying around a lot faster. And because the volume is fixed, it will not adjust, it will not move. Basically, what that's going to cause is a lot more collisions to occur. And what we will see is the pressure will go up as well. And vice versa, if we lower the temperature, our gas molecules are going to be flying around a lot slower, going to lead to less collisions occurring, and less collisions will lead to a less pressure happening in that situation. Now, with Charles' law, because it's able to basically maintain constant pressure, the way it's able to maintain constant pressure is really the volume. So it's the volume there that's able to adjust to really allow the pressure to remain constant. So when we do increase our temperature in this situation, even though our gas molecules are flying around a lot faster, what will happen in this case is the volume will actually increase with it. So even though they're moving faster, we're still going to have basically the same number of collisions that's going to occur, and that's going to allow the pressure basically to remain constant. So in Charles' law situation, as the temperature goes up, we do expect the volume to go up as well, and also vice versa. As we lower the temperature, our gas molecule is going to be flying around a lot slower. And again, because they're flying around a lot slower, what happens with the volume is the volume comes in on them, and that again allows the number of collisions basically to remain constant. And thus we will actually see the pressure remain constant in this case. Now, also really important, not just for these two gas laws, but pretty much any gas law that you deal with here. We saw the relationship when you graph volume versus temperature in this sort of situation. It always hits the same number, and that was minus 273.15 degrees Celsius. And basically that is how we convert it to Kelvin. So pretty much if it is a gas law, you need to make sure the temperature is always in Kelvin. And once again, that is the Celsius plus a 273 to convert it into Kelvin. Again, even if the problem gives you everybody in Celsius and they ask you to give the answer in Celsius, you do have to convert it to Kelvin before you put it into the gas law. And then afterwards, you need to convert it back to the units that you need. Any questions on any of that there? I think that's where we left off, if I'm not mistaken, I hope. So I don't think we did this example, right? Did we? We did not. Okay, so let's do this example here. Okay, let's take a look. So as I mentioned, I think earlier, when you're dealing with gas law sort of problems, it's a really good idea just to pull out the information from the problem. So in this particular case, we do have a volume that is 452 milliliters. It is heated from a temperature of 22 degrees Celsius to another temperature that's 187. And we are looking for a volume here. So again, we do have several to choose from at this point. We have our Boyle's law. We have our Charles law. And obviously here, we also have our Guy-Lussac's law. And just quickly, just pulling this information out, you should be able to see that really it is obviously Charles law here that really does fit with what we got going on. We do need to make a couple of conversions like normal here with our temperature. So we do want to add 273. So that's going to be 22 plus 273, going to give us 295 on this guy. We got 187 plus 273, 460 on this guy here. At this point, V1 T1 is equal to V2 T2. In this case, we're solving for V2. To move T2 to the other side, we're going to multiply it. Or again, it basically ends up in the opposite location of where it was. So that means V1 T2 divided by T1 equals V2. Putting in our numbers in the correct location here gets us 452 milliliters. We got T2 up on top, 460. And we got T1 on the bottom here, 295er. That's going to cancel out our kelvins. That's going to leave our volume here in milliliters. So 452 times 460 divided by a 295er, going to give us something like 705 milliliters in this particular case. Any questions on the calculation here? We also remember can kind of make sure that our numbers sort of make sense. Our answer, yeah. Personally, I use 273, and most people use 273. You can technically use either one as you want. The real number is 273.15, but most people round it to 273 because the 0.15 oftentimes gets rounded off anyway. So I'm good with 273, but if you want to use a 273.15, either one's fine. Yeah. Other questions? Okay, so we can kind of make sure it makes sort of sense here. In terms of here, we do see that our temperature increases, which means we should expect that the volume would increase as well. And it went from 452 to 705. So again, this is a good way to maybe check, because it is very common when people are doing gas law problems, they oftentimes will invert numbers a lot of times, have like T1 and T2's place or something like that. So, you know, if you ended up here with a volume that was less than what you started with, based on what you know about Charles law, that would not make sense. It's a good way to kind of check yourself. Not necessarily that the number is right, but at least it's in the right direction. Any questions on that there? Okay. All right, so that's the one we just did. All right, so another law, our good friend Avogadro, you know, he had a number, but, you know, he really wanted a gas law, I think. So Avogadro, when we think about Avogadro, we think about Avogadro's number, which is 6.022 times 10 to the 23 equals basically 1 mole. So it's not surprisingly here, Avogadro's law basically deals with moles. It is, as we see down there, V1 N1 is equal to V2 N2. And basically, this is actually at two different conditions. This is at constant pressure and temperature. So constant pressure and temperature, Avogadro's law kicks into gear here. The V's are volumes. And again, they could be any unit you want in volume as long as they are the same. And N here is moles. So N is the number of moles for our gases. And we can use this just like any other gas law. Obviously, if you have 3 of the values, you can find the 4th value as well. Sort of a important relationship that comes from sort of Avogadro's law is basically the number of moles is sort of proportional to the volume. What can happen is when we have Avogadro's law situation occurring and we have a situation at constant temperature and pressure, we can actually apply it to how we do stoichiometry. So we'll talk a little bit about this in a bit, but if we had, say, something like this, 2A plus 3B, and they're all gases here, goes to 2C. Now, if we were going to do some type of stoichiometry problem, what it normally will involve, as we'll talk about, is somewhere along the way, you got to use a gas law and basically stoichiometry together. And we could use our normal mole-to-mole relationship. So 2 moles of A is equal to 3 moles of B. 2 moles of A gives us 2 moles of C, and so forth. Now, if we happen to be under these conditions here of constant pressure and temperature, we actually could do a volume to volume relationship because it works basically the same way as moles to moles. So we could, in this case, for this equation, say we have 2 liters of A gives us 3 liters of B. We could say we have 2 liters of A gives us 2 liters of B, and 2 liters of A, B, 3 liters of B gives us 2 liters of C. So we could do almost a volume to volume relationship, just like we do a mole to mole relationship if we were under constant pressure and temperature. The benefit of that is later on when we talk about stoichiometry, it may allow you not to have to do necessarily a gas law in there as well. You kind of go right into the stoichiometry part. But using Avogadro's law like it is there, V1 over N1 equals V2 over N2, again, you can just plug and chug in there. Sort of a side effect of Avogadro's relationship there is it's sort of the stoichiometry part allows you to do that. And that's what we see here. Basically, we get 1 volume for 1 mole, 2 volumes for 2 moles, 3 volumes for 3 moles. So this allows us basically to do sort of a mole to mole relationship, doing a volume to volume relationship as well. We'll get into that a little bit later on in a bit here. So let us take a look at putting all these gas laws together. Boyle's, Charles, Avogadro's law gives us the ideal gas law, and the ideal gas law is PV equals nRT. And the ideal gas law is a little bit different than some of the other gas laws, obviously, we've been talking about. First off, it is sort of a one and done situation. There's no 2 pressures, no 2 volumes, no 2 temperatures. So you just basically have one of everything that's there. It also is pretty much the most restrictive in terms of units than any gas law. So when you use the ideal gas law, everybody has to be in specific units in order for it to come out correctly. The pressure here needs to be in atmospheres. The V, our volume, needs to be in liters. The N needs to be in moles, and our temperature here needs to be in Kelvin. And really the reason for all that is the value of R. R is the gas constant, and it's a value that you always have, which is 0.08206 liters atmosphere Kelvin mole. Now, a lot of books and stuff use more of a rounded number these days, 0.0821, which is perfectly fine as well. I use the top number because that's what they beat it in my head and I can't get it out. So that is the number I use, but a lot of books and stuff will kind of use this rounded number a lot these days. The good news is you always have that number, although in a lot of problems, they don't tell you that in a sense. So they assume that you have that number available to you. So in a lot of problems, they will not give you R or anything like that. So that's a number you do need to know when you do these type of problems. So what is an ideal gas? Well, there's a couple of things that make things an ideal gas. And there's really 2 things that we look at. So under normal conditions, an ideal gas is a gas where the volume of the gas itself is small compared to the volume of the container it's in. So if you look at a lot of gas problems that you read, a lot of times they'll talk more about the volume of the container the gas is in rather than the volume of the gas itself. So compared to the container it's in, the volume of the gas is really negligible. And the idea there is the gas molecules are flying around, which means they should fill the container uniformly, which means that the volume of the container is essentially going to be the volume of the gas in that situation. The other thing that makes something sort of an ideal gas is the idea of when you have different gas molecules in a container, there really is no interaction between them. So what that means is in normal cases, when molecules get near each other, they either repel or are attracted to one another. So in sort of an ideal situation, the idea is even though there's multiple different gas molecules in the same container, there's really no attractive force, no repulsion force between them. You almost could think of those gases as being in the container by themselves. And that's what we deal with as we'll talk about sort of partial pressures and stuff like that. Is that ideal in an ideal situation? And that normally is the case for most situations that you deal with. Only when you get into really extremely large pressures or low temperatures do gases really not sort of behave this way. And you do have to take into account things like interaction between different gas molecules and the volume of the gas itself. Those are what are referred to as real gases, and you'll talk about them in 1A. We don't really talk about them here, but under our conditions, we assume sort of the ideal condition for most gases that are there. A couple other really important sort of relationships as well is we'll start with this, which is STP. So once again, STP does stand for standard temperature and pressure. And once again, when they do say STP, they do represent values. So the temperature is 273 Kelvin and the pressure is 1 atmosphere, or obviously its equivalent, 760 torr, 760 millimeters of mercury. So when you're given something that says, you know, what is the volume at STP or something like that, those are the values of temperature and pressure that you could use in the calculation. If it is not 273, it is not 1 atmosphere, then it is not STP. So those would not be the conditions. Now, there's a really nice relationship that you could use when a gas is at STP, and it has to be at STP. So 1 mole of any gas, 1 mole of any gas, there you go, equals 22.414 liters at STP. So once again, that is the really important part, which is it does need to be at STP in order to use this conversion factor. The reason why you might want to use this conversion factor is you can use it and not have to use the ideal gas law. So this is a situation where you can maybe avoid the ideal gas law, but once again, it definitely has to be at STP conditions in order to use that equation. If it is not STP conditions, you should not be using that conversion factor at all. So it is only under those specific conditions that you can do that. The good news is PV equals nRT. The ideal gas law, you could use under any conditions. STP conditions, you just put 273 in for the temperature, you put 1 atmosphere for the pressure, or any other conditions that's non-STP conditions. So if you don't want to worry about maybe using this incorrectly, just use the ideal gas law and you'll be good in any situation. So it's sort of a universal sort of equation that can be used pretty much for all gases in multitude of situations. So when in doubt, use the ideal gas law, but if you definitely are sure you're at STP, you could sort of sidestep the ideal gas law and use that conversion to do it. Any questions on that? That, by the way, is how we get the gas constant, by putting into the ideal gas law and solving for all of our ST conditions. That would mean the temperature is 3, the pressure is 1 atmosphere. We have 22.414, and that's essentially where the gas constant comes from, that number. All right, so let's try one here. Calculate the pressure in atmospheres divided by 1.82 moles of SF6. You have moles, which is 1.82. We do have a volume, 5.343, and we do have a temperature which is 69.5 degrees Celsius. So again, if you just pull out the information, obviously none of these earlier gas laws would work since we only have one of each of those informations. Really, the only one that would sort of fit, obviously, is our ideal gas law. And this is what I was talking about earlier. Again, they really don't usually make any mention of the gas constant. They just assume that you should know, and you should know this value here. And you always have that, again, sort of given to you or available to you to use. So when looking at all this stuff here, we do need to use PV equals nRT. We're going to solve for P. So we're going to send V to the other side by dividing V to the other side. That gives us P is equal to nRT over V. We need to look at units. So our moles here are already in moles, so that's good. Our volumes in liters, so that's good. So once again, very common here. We still need to do that temperature conversion. 342.5 Kelvin. Now we do have, whoops, 0.5 Kelvin. Now we do have everybody in there that we need in the right units. So put in our numbers in, 1.82 moles. Our gas constant 0.08206 liters atmosphere Kelvin mole. Squeezing in my temperature here of 342.5 Kelvin divided by our volume, which was 5.43 liters. In terms of units, the moles on the bottom and top cancel, liters on top and bottom cancel, and my Kelvin over here cancel. Leaves me just atmospheres just left over there from the gas constant, which is good since it is a pressure we're looking for. 1.82 times 0.08206 times 342.5 divided by a 543er, going to give us a 9.42 as our pressure here in the atmosphere. First off, any questions on the calculation part? Yeah. Say one more time. The value. Yeah. Exactly. So the gas constant basically has all four of those units, if that's what you're asking, and it is liters times atmospheres up on top, divided by Kelvin times mole on the bottom. The good news is if you remember that, that also will remind you when you're using the ideal gas law, what everybody else has to be in terms of units so that everything properly cancels out. But that's how we're left with, what's the units that are left. In this case, we had Kelvin on the right there, and we had moles up on top. So the Kelvin canceled, the moles canceled, and then we were dividing by liters on the bottom. So those canceled, and that left us the atmospheres that was left over in terms of the units in this case. Yeah. Other questions? Now, also a variation on this would be for the moles. It is also very common that you're given that information in grams. So doing grams to moles conversion using the molar mass is a very common thing that you also have to do in an ideal gas law situation. And again, the molar mass from the periodic table allows us again to go from grams to moles. Those are very common things. The other is again, in addition that you going from grams to moles, obviously our Celsius to Kelvin. Milliliters to liters is also a very common conversion that you need to use when you're doing this stuff. A reminder that 1,000 milliliters, right, is 1 liter. So that's a conversion that sort of popped to get the volume into the correct unit. Because as you basically collected the gas in milliliters, common obviously, volume is collected in. So getting it into liters is used a lot. Any questions on that there? Yeah. All right, so let's talk about another important gas law. If we sort of take the ideal gas law and we actually solve it for R in two different situations, because R is a constant equal to each other. And for the most part, the remains constant unless you open the top of it, I suppose, the container. Then this really does sort of reduce down to what is sometimes referred to as the combined gas law. So the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. So in terms of this gas law here, we really do have all three variables happening at once. Our pressure could be any unit on both sides. Again, as long as they are the same unit of pressure. It could be any unit of volume as long as they're the same on both sides. Once again here, like every other gas law, our temperature does need to be in Kelvin here. So the combined gas law is a good one. P1 V1 equals P2 V2 over T1 V2 in each case. And the reason for that is if you remember this gas law, it can be really helpful to not have to remember like all the other gas laws. More specifically, if you remember sort of this relationship, which is basically P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. You pretty much could get any gas law you want out of this one. So for example, let's say that we had no mention of temperature or temperature is constant and no mention of moles. We basically just scratch those guys out, and now I have Boyle's law basically right there. If we take this same one and we want to throw the end in there, you can or not. If we have mention of nothing about pressure or moles, you basically scratch out the pressure on both sides and the moles on both sides, and now you have Charles' law. If you have no mention of volume on both sides, or it's constant, scratch out the volume. Also no mention of moles, you can scratch out the moles, and now you have basically Guy-Lussac's law. And lastly, if you have no mention of pressure or temperature, you scratch out the pressure on both sides, scratch out the temperature on both sides, and now you have Avogadro's law. So if you got to invest your time to remember equation, P1 V1 N1 T1 is equal to P2 V2 N2 T2. Obviously, in the combined gas law situation, no mention of moles. You just scratch that out, and you have obviously the combined gas law as well. So I would invest in remembering PV equals nRT, and invest in remembering P1 V1 N1 T1, P2 V2 N2 T2, and pretty much you should be able to get any gas law that you need from those two equations. Just scratch out whatever is not mentioned or whatever is held constant, and then you'll have what you need. Any questions on how to do that there? Yeah. All right. On here, consider a simple oxygen gas at 27 degrees. It has a volume of 9.55 liters and a pressure of 2.97 atmospheres. We check, so once we got a temperature that's 27 degrees Celsius. It has a volume that is 9.55 liters and a pressure that is 2.97 atmospheres. We are going to change the pressure to 8.25, and we're also going to change the temperature there to 125 degrees Celsius, and we are looking for volume. So once again, just by pulling out the information, it really combined gas law that we saw, which is our P1 V1 T1 is equal to P2 V2 and T2. In this case, if you memorize the other one with the moles in it, there's no mention of moles. You just scratch it out, and obviously you would get here to this equation. In terms of pressure, we're okay. They are both in the same unit. Once again, if they are not in the same unit, you do need to pick a unit and get both of them obviously into the same. Our temperature here, we're going to convert to Kelvin like normal here. So we're going to do a 273 on this guy, going to give us 300 Kelvin, and we'll do a 125 plus a 273 gets us 3. We basically can call the first set ones, the second set 2s. And by the way, in reality, it doesn't really matter which 2s, as long as you keep all the information that goes together. We're actually looking for V2. So a reminder that sort of a quick way you can rearrange these equations is since the T2 is on the bottom, it will end up on top. And since the P2 is on the top, it will end up on the bottom. As you go across the equal signs, we're basically multiplying and dividing those to the other side. That would then give us P1 V1 T2 divided by T1 P2, leaving our volume by itself on top, which is what we want in that case. By the way, anytime you have anything that's sort of an equal sign, basically to quickly rearrange, they just go in opposite locations. Again, as you go across the equal sign, it's basically how you do that. Putting everything in the correct location here, our P1 is 2.97 atmospheres. Our V1 is 9.55 liters, and our T2 goes up on top, 398, divided by our T1, which is 300, and our P2, which is 8.25 atmospheres. Atmospheres on top and bottom cancel. Kelvin on top and bottom cancel. Once again, leaves us liters as our unit that's left over. And that's good since it is a volume we are looking for. So 2.97 times 9.55 times a 398 divided by a 300 and divided by an 825. Going to give us a 4.56, I believe. I read my thing right there. Liters as our unit here. Any questions on that calculation? I would say this is the one that gives people a very hard time, is the rearranging part of it. It's very common. People kind of revert things and stuff like that. So again, the quick way is just to move it to opposite sides of the equal sign. But again, if that's an issue, you might want to take some time to make sure you know how to properly, obviously, rearrange these equations. Any questions on that there? Okay, the next thing we're going to talk about is geometry that involves gases. The good news is it's pretty much the same steps that we use in a normal stoichiometry problem. So remember, in a normal stoichiometry problem, we always want to balance the equation. We want to convert to moles. We then want to do the mole to mole relationship. And then we want to convert moles into some other unit. Also remember that somewhere along the way, if it is a limiting reagent problem, right, we also want to determine the limiting reagent if needed. So in these type of problems that involve gases and stoichiometry, it really is the same sort of steps. And in most cases, the difference is how you get to moles, or what you do with the moles at the end of the problem. So somewhere along the way, you usually will use PV equals nRT. And a lot of times that happens in step number 4. And a lot of times you are interested in a volume. So a lot of times at the end there, instead of using molar mass at the very end to figure out how many grams you made or something like that, much like what you did in class, you were interested in how much volume of gas you collected. So that's a very sort of calculation that you do at the end. You also could use it sort of early on up here to, instead of converting grams to moles, you could use the ideal gas law and solve for N, which would be PV over RT, and you would be solving for moles. And then at that point, it would be a normal sort of stoichiometry problem. So those are two very common places where you have to sort of insert perhaps the ideal gas law. I would say probably in most cases, using it at the end there with volume is very, very common. But like we did, I think in the second experiment that we did, you actually need to use the ideal gas law up front, right, to get the moles, and you need to back calculate that way. So it can be used in sort of either direction. You can, again, also have a limiting reagent type situation that could occur in a gas stoichiometry problem. And it's really the same situation as what we talked about earlier. If, again, you have enough information for both reactants to get to moles, then you do need to do that extra step of figuring out the limiting reagent. If you don't have enough information to do that, you could assume it's a basic stoichiometry problem and just roll through these steps. So with that being said, why don't we try one here? What volume of hydrogen gas at 27 degrees Celsius and 1.25 atmospheres is required to react with 5.65 grams of phosphorus? Let me give you some numbers here. Phosphorus is 3097, I think, from the periodic table. Hydrogen here is 1.008. All right, so give it a go. Try it out there. You need basically the 4 stoichiometry steps somewhere along. Okay, let's take a look. We're going to pull out some information here. We're looking for the volume of hydrogen gas. We do have the temperature there, which is 27 degrees Celsius, and we do have the pressure, which is 1.25 atmospheres. Remember, we really always have R as well if necessary, which it will be in this case. Now we pretty much can see the ideal gas law, and that is what we want to really use here for hydrogen gas, and we are looking for the volume. We already have the temperature, we have R, and we do have pressure. So the one thing that we're sort of missing for the hydrogen gas here is the moles, and that's really where the stoichiometry come from. So we're going to do in this case a basic stoichiometry problem so that we can calculate the number of moles of hydrogen, and then we'll have everything that we need basically to go into that gas law. So again, following our steps, we would want the balanced equation, which I think by changing that to a 4 we now have, so that's good. Next, we want to take whatever they gave us and convert it into moles. So in this particular case, the temperature and the pressure obviously is related to the gas, so we're not going to worry about that. So really the only other piece of information that was given to us was the grams of phosphorus. So that's what we want to convert into moles. So starting with our 5.65 grams of P4, using the molar mass here, would be 4 times 3097 grams per mole of P4. And if we do that, we end up with 5.65 divided by 4 times 3097. That gets us 0.045609 moles of P4. So remember that this is the moles of P4, but we really are looking for the moles of hydrogen. So that's where the stoichiometry comes in. So we convert it to moles. Next is the mole to mole relationship. So from the equation, we see for every 1 mole of P4, there is 4 moles of H2. So the stoichiometry there, 1 mole of P4 gives us 4 moles of H2, which means we'll just do our stoichiometry here. And obviously, if you didn't want to get an answer, you didn't need to, you could just continue it on. We would get 1 mole of P4 on the bottom, gives us 4 moles of H2. So again, these cancel. We're going to times that by 4, and that's going to give us basically 0.182 moles of H2. Any questions on that there? So it really is sort of the basic stoichiometry steps, and really 4 here, like I mentioned before, is to take the moles and convert it to some other unit. So very commonly, like we just talked about here, we're not going to use molar mass, but now we have everything we need to use the ideal gas law. So we're just going to use the ideal gas law here. So PV equals nRT. We're looking for a volume. So volume would be nRT divided by P. We want to make sure everybody's in the right units. So pressures in atmosphere. So that's good. Like usual here, we do need to convert our temperature. So we'll add a 273 to our 27. Gives us 300 Kelvin. And everybody else should be in the right units at this point. So using the moles we just calculated, 0.182 moles. Our gas constant and our temperature converted to Kelvin divided by our pressure, which was given to us at 1.25 atmospheres. So moles cancel, Kelvin cancel, atmospheres cancel, leaves us liters as the only unit left, giving us 0.182 times 0.08206 times a 300 divided by a 1.25 gets us a 3.58, I believe. If I punch that in right, 3.58 liters of H2 in this case. Any question on any part of that calculation there? So gas stoichiometry problems are really no more than regular stoichiometry problems, but again, somewhere along the way, in most cases, maybe twice or maybe at least once, you'll have to use the ideal gas law. Any questions on that? Based on the information, so in this particular problem here, gas information, which is the temperature and the pressure, given basically grams of phosphorus. So because the phosphorus here was a solid and not a gas, we didn't need to use the ideal gas law on the front part to get to moles. But if it was maybe something like you were starting with oxygen gas or something up in front, then you might have had to use it, to do it that way. So I would say usually if it's not sort of two gases going from one to the next, you probably wouldn't use it twice. You would either, in most cases, either use it up front and not on the back end of the calculation, or on the back end of the calculation like we did here, not up front. But if you had two gases, potentially that would be the case where you use it twice. Yeah. Other questions? Okay, we will lay it up there for now.